Okay. Any questions on what we did up to this point? Okay, now this is basically, this equation is the key equation that we are going to use for the remaining implications. Now the remaining implications are again not I'm not going to prove the theorems because the theorems are quite simple, but I'll just explain how it is done. Okay, so let's understand the implications. This is using this equation actually. Now, the first implication is, now a policy with the manufacturer allowing unlimited returns. Now, by the way, now what we would usually want to do in this type of a system is to achieve a Q which is equal to QT star, because we know that that will maximize the expected profit of the overall system. Now, of course, by selecting different C1, C2, and R values, the profit distribution is going to be different. Okay? And in some cases, manufacturer is going to get a large percentage of the share, whereas in some cases, the retailer. But the idea is that we always think as analysts that if we can create the environment where we are going to have the maximum benefit, they will find a way to share that maximum benefit. So this is more or less the idea which is sought here. So implications are always going to have this starting point in mind. So a policy with the manufacturer allowing unlimited returns for full credit. What do we mean by full credit? C2 is equal to C1 is system suboptimal. Now, this policy is actually the policy which is used by the printing houses like newspapers. For example, if you are a retailer, if you are selling, if you are a news vendor, actually, all the newspapers that are going to come forth in that day is going to be returned in full credit, for full credit. So you see that actually this is system suboptimal given, of course, the structure that we have here. Why? Let us see this. How are we going to see this? Well, first of all, what is the implication of unlimited returns? R is 100%. So R is equal to 1, actually. And C2 is equal to C1. So how can we show that this is not something which is desirable? We're going to look at this equation. So let me call this equation star. Okay? That's the key equation. That's equation number 10 in the paper. Okay, so according to star, if I place R equal to 1 and C1 is equal to C2, what am I going to have? I'll have minus C1 plus P plus G. Then I'm going to have minus F of Q star times P plus G minus C1. I have replaced C2 with C1. And then R is going to be 1. So note that this term is going to be 0. So I'm not going to have any other term left. This should be equal to 0. Now, what can you say? If you look at this, what do you see here? Okay, so what is this? FQ star is equal to 1. So in this policy, the retailer is going to order infinite amount, okay? Which is probably not something which is desirable. Because the news vendor has nothing to lose. That's the reason why the newsstands actually are not operated this way. They don't allow any newsstand to order the quantity that they want. What Hürriyet, Milliyet, and others would do will be simply distribute certain amounts, and they will always control the amount that they distribute. Okay, because if you leave it to the news vendor, okay, news vendor is going to be inclined to order infinite amount. Of course, then the system becomes a vendor-managed inventory type system, which is a different ballgame. Okay, so this is implication number 1. Implication number 2, a policy of a manufacturer allowing for no returns is system suboptimal. So if I don't allow for any returns, then that will also be system suboptimal. We can find it from here. If you take R is equal to 0, this is going to be f of q, okay, times C2 minus C3. And I have f of q here as well. So this is going to become P plus G minus C3, because C2s are going to cancel each other. Okay, so this is going to be minus C3. And here I have C1 plus P plus G. And we are going to see that there is something contradictory here. So this is not possible because C3, which is the salvage, excuse me?
Less than zero.
C is less than, yeah, always C1. And then this is not going to be, of course, acceptable. Okay, so this is theorem 2 actually, but the idea is that you simply play around. If you look at the appendix, it's like only 4 rows, okay? You can see that by playing around, actually you obtain those conditions are violated. Remember the conditions that we wrote for C's here, they are going to be violated. Now, eventually, let's move to the last implication. I think this is sort of an important implication, or this is the form that you can place. Now, let's say that you want to obtain unlimited, you want to give unlimited return possibility. Okay? So a policy with unlimited return possibility at partial credit will be system optimal. Now, of course, you have certain other optimal solutions as well. In other words, system optimal solutions. There are a number of different, because what you have is you actually have 3 parameters here that determines the optimality conditions. Okay? So by changing any of those 3 parameters, you can obtain a different set which is going to yield the same result. You have 1 equation, 3 unknowns actually. So you can play with them in any way you want. So if I take R as unlimited, which means that R is 1, in that case, the condition that I'm going to obtain will be simply C1 is equal to P plus G. Excuse me, I think what I missed is the following, probably. Now, I am, of course, going to require this Q star to be QT. So I'm not actually using this equation specifically. Remember the QT star? I think I have erased. But remember model 1? I obtained a QT star with certain ratio. Okay? So I want this Q star to be that QT value. So what I impose is now I impose FQ star to be that ratio. So you have to replace FQ star with that ratio in order to understand these implications. Okay, I didn't do that. So we cannot directly see it from here, actually. Okay, and so what you have is you have this condition, PG minus P plus G2 minus C, and P plus G2 minus C2 divided by P plus G2 minus C3. Now, what this is simply the following. If I am allowing for unlimited returns, okay, this C, given a C2 value, if I select C1 like this, okay, I'm going to obtain the system optimal solution. So this is a relationship between C1 and C2, and all the combinations of C1 and C2 will give me the system optimal solution. So give me a C2, I'm going to find my C1 from here, and that is going to yield an optimal solution. Of course, you have the boundaries, remember? C1, C2 cannot be greater than a certain value. So within those boundaries, you have infinite combinations of C2 and C1, which is going to yield the system optimal solution. Of course, for each C1, C2 combination, you are going to have a different division of profit between the retailer and the manufacturer. Okay? So there are some numerical examples in the paper that shows that. Now, why is this nice? Because it turns out that in real life, of course, information is not symmetric. In other words, the manufacturer will never know the costs of the retailer. Okay? There are certain costs occurring there, but they wouldn't know that. The demand function would not be known unless you have a new thing coming into picture, which is going to disclose the demand structure that the retailer is seeing. Now, given all of these, we usually have in real life decentralized systems, so that we cannot do much. But what the manufacturer would do would be to use a scheme like this. For example, the manufacturer will go to the retailer. There might be more than one retailer. Let's say that they are not competing, but there are many retailers, like the newsstands. They usually don't compete with each other because they are far away, practically speaking. So what you can do is, given this approximate computation, the manufacturer may offer the retailers a menu, many of possibilities with respect to what they want. They are going to say that we are going to offer you unlimited returns, and we have C1, C2 combinations, and just select any one that you want. Okay? So the idea here is that, note that these parameters here is not a function of the demand function itself. Okay? So this is clean of the demand function. Okay? So I can now create a menu of contracts, actually, and where I will have different C1, C2 values, and I will let the retailer select the one which she opts the best among the others. Okay? So in reality, actually, remember in the beginning I told you that C1, C2R actually looks like a contract, but you want to be a little bit flexible, and you can create menu of the contracts. Menu means that you have options, actually, within the contract structure. Okay, and this C1, C2 values can be computed in this fashion. And this is a case where things are actually not very complicated. And so this menu, the selection of, if a retailer selects a certain value, actually it's not going to be different. Only the cost, the profit division is going to be different. But of course, the retailer doesn't know the C value as well. Okay, in other words, the retailer doesn't have the manufacturer's information as well. So things are not going to be that simple. But at least these type of menus are used in order to get some information out of the retailers. Because you can go back, and if the retailer selects a certain C1, C2 combination, then it might reveal some information with respect to the goodwill cost. It might reveal some information with respect to the operational costs of the retailer. So there are certain contract structures which are going to reveal information. And this is the reason why contracts are very nice tools with respect to decentralized structures, because it's a very good way of communication. Now, in this case, of course, this menu is not going to bring any additional information. Okay? In this case, it's a straightforward case. But the idea here is that, again, you can have different C1, C2 values, and when you change C1, C2 values, of course, you can see from here that the manufacturer is going to have different profits. Yes?
In this equation, I think the G2 value in the term with C2 will be G.
Okay. Yes. Good. How did you find it out?
Multiplied.
Okay. 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 Okay, any questions on this? Now, if you can read the paper is quite easy to read. And there are some examples, numerical examples, where you can see this profit division. Okay. Now, let's go one step further now. And let's talk about some issues which are going to follow, actually, this work. Now, we are going to see another paper, which is, again, a pretty nice paper, where we have a different type of an environment. But the ideas are going to be the same, but there we're going to have some kind of a contract structure. And we're going to see what that contract structure is. Now, number one, we didn't do any optimization on the manufacturer. But now, if information is available, manufacturer can go ahead and maximize its profit, its expected profit. And then select the parameters of the contract accordingly. Okay? Now, this type of a game, this is a game actually, it's called leader-follower game. Okay? And why do we call it leader-follower game? Because basically the leader announces some prices, C1, C2, R, some parameter values, and the retailer actually follows with the optimality equation. Okay? Rational. If the retailer is a rational actor, okay, follows with that optimality equation. So uses that and orders accordingly. Now, if I am the leader and if I know the quantity that the retailer is going to order, given my parameter values, then I can play with those parameter values and optimize my own expected profit. This is called the leader-follower game, or a more correct name is, it's called a Stackelberg game. Okay? This is sort of one of the topics that you see in game theory. Okay? It's a Stackelberg game, which means that you have. But of course, in reality, you don't have this information availability. And this is important. Now, this paper tells us certain things about contract design. Now, why do we design contracts? Now, there are many different reasons for designing contracts. Of course, legally speaking, you want to make sure that both parties keep up with their obligations. That's the regular meaning of contract, actually. In practice, actually, when you talk about contracts, everybody would speak about legal obligations. Of course, the contract that we're talking about is also part of the legal obligation, but we are talking about contract design with respect to the economics. We want to design contracts or contract structures so that we will be able to get the system optimal solution as a result of the application of the contract. In other words, if you are operating a supply chain or within a supply chain, you want to have a contract where eventually you are going to get the system optimal solution, which means that the total profit in the system is maximized. Now, of course, that contract will implicitly obtain or have the way that we are going to share the profit. Okay? But still, I think in general, as an idea, economically designing contracts means that contracts that will yield the system optimal solution as a result of the contract parameters. Okay? This is the reason why we want to design contracts. So economically designing contracts, so a contract that will naturally yield QT optimal is what we are looking for, actually. Naturally means that, okay, naturally means that everybody, each actor is trying to optimize their own objective function, okay? But as a result of this, whether we have Stackelberg equilibrium or Stackelberg game or any other game, okay? As a result of this interaction, we want a Q quantity to come up which is identical to the system optimal. Okay? Now, if you have a contract mechanism, now in this case, for example, C1, C2, R is a contract mechanism. Okay? If you have a contract mechanism like this, then you can obtain system optimal solution under certain circumstances, of course. Now, what are the assumptions? The assumptions are that both actors are going to be sort of rational with respect to their own objective functions, and their objective functions should be part of the system objective. In other words, the way that you measure performance is going to be in line for both parties. Expected profit in this case. Any questions on this? Now, we're going to talk about these a little bit more, but one thing that you should be sort of worrying in this type of system is that you have the so-called information asymmetry. In other words, not all the parties are going to have all the information related to the other party. Okay? Manufacturer may not know the demand. Retailer may not know the manufacturing costs. Retailer may not know the salvage value even. Okay? The retailer may not know certain things about the manufacturer, so on and so forth. So there is always an information asymmetry, which makes all these contracts, of course, more important, because basically the risk that you take without the contract might be even more. So contracts in that respect are very reasonable. By the way, just to give you an idea, in practice, the contracts have two parts. Actually, the contract, the body of the contract is definitely a legal document. Okay, so you have, let's say, 20 pages where you write, for example, this is basically this party should give the other party the quantities that the first party is asking for on time, certain things, these are the penalties and so on and so forth. So this is basically a completely legal document. But what the companies have been doing in the last 10 years is that they have some appendix which makes the contract very similar to what the contract types that we're talking about here. For example, they talk about how are you going to get the information which is relevant for the contract. For example, if one party says that I'm sending every month, I'm sending 10 units using a certain, let's say, Yurtici cargo, and then the other guy is telling that, well, I'm only receiving 9 every month. Okay? Now, how are you going to solve this? There should be a common information base in order to make the measurements first. So these legal contracts in their appendix, they start with certain definitions. They start with, then they continue on with the information sources. For example, which is the information that should be used in order to understand, to figure out whether contractual agreement is satisfied or not. Now, are we going to allow the manufacturer's database to do that? Probably not. The retailer's database? Probably not. Then there should be a way of finding the correct information. Okay? That's the reason why you have third-party logistics firms coming into picture, because they are usually the ones who keep the information. So I'm talking about a legal contract, but the appendix starts with this, continues with the information, then gives, for example, definition. Like the retailer wants a certain service level to be attained, okay? And then they give the definition of the service level. How is it going to be measured? It's a formula. Okay, one of the formulas that we know. But basically, it talks about how is it going to be measured. For example, when are we going to get observations? Is it at the end of the day, at the end of the month, continuously, so on and so forth? You specify the dates. Everything is specified. And then you specify certain other things in a lot of detail. And it turns out that that technical appendix, I will call it a technical appendix, is like our technical papers. But certain things are very well defined, very clear and open. That you don't have any derivations there. But you have everything which comes as a result of derivations, the parameters and so on, given there with the definitions. And to prepare something like this is not very easy. For example, I have seen one document by Philips. The appendix was 50 pages long. This was sort of a standard contract that they sign up with their suppliers. And it's not because basically they want their suppliers to lose money, but basically to make sure that business is understood and everything is well measured. Of course, there are a number of different key issues. There are maybe 4 or 5 parameter values which are given in that appendix, which comes from work like this, actually. So they set those parameter values according to the work that we do here. So you can see how this is going to be utilized, basically. And you have very little thing left for the court. If you're talking about, for example, if you go to the court because of the service level, there is nothing that the court would do other than simply saying that, give me this information source, measure this, measure that, let us see who is correct. So it becomes very easy. Now, there are many reasons for doing this in that detail, because they want to make sure that the things run fastly. They don't want to wait a court to give a decision after 5 years. So they want to make sure that technical issues are defined and resolved in the beginning. Now, what is our role? Our role is not to prepare that, probably. To prepare, I mean, is probably something which is like preparing a manual. But our role is to come up with those parameter values which is going to take place in the contract. Okay, so this is a very serious issue, and I think in the next few years, probably most of the Turkish companies are going to do it this way as well. They already started it, actually. There are certain companies that are preparing detailed contracts just to make sure that they can resolve things before going to the court. They don't want to the court. They don't want to go to the court because courts are usually very slow. Moreover, if you are doing business internationally, okay, and even there are a lot of ambiguity with respect to which court is going to be responsible. Let us say that you are doing business with a Swiss company, okay? You have a truck in Yugoslavia that broke down, okay? And that's the purpose of the delay. Now, which court is going to be responsible is not clear in the international law. It can be the Yugoslavian court, it can be the Swiss court, it can be the Turkish court. Even if you write this court is responsible, if there is an incident around the world in an international territory, nobody knows who is going to be responsible. So there are things of that sort. So that's the reason why contracting in practice also is becoming very important, because they want to resolve these type of issues. Now, for us, on the other hand, the way that we see contracting is, we see contracting as the relation between two entities. So we are looking for, rather than looking single location type problems, in supply chains we look multiple locations, and contracts are structures that bring those multiple locations together. So, and that's the reason why we want to analyze them. Okay, now the fourth issue, which is probably missing here, is the existence of competition. Now, in these type of systems, you might have two retailers that are close to each other, and they might be competing for demand. Okay? In that case, how are you going to solve the problem? Well, it turns out that the solution of that problem is becoming even more difficult, because usually what you have is you have two levels of gaming. Now, once all the quantities are sold to different retailers, the retailers game for the demand in the market, because they can both reach the demand. So there is a game there, and at the top of that there is a game in between the actors and the upper level, which is the manufacturer. So it turns out that when you have competition, the analysis is going to take you to so-called Nash equilibrium type problems, where Nash equilibrium is the equilibrium between entities that are doing the same thing. Whereas Stackelberg game, or Stackelberg equilibrium as called it, usually occurs when you have actors at different levels doing different things, like one of them is the supplier of the other, so on and so forth. So these are the things that are important, but we don't see it, of course, in this paper. This paper is just introductory. Now, we are going to see certain things about this in the next couple of papers, but this is there are a large number of papers related to these issues. I would say probably hundreds, or maybe maybe thousands of papers on this topic, although it is a pretty new topic. Okay. Okay, any questions on this? Okay, now let me talk about the next paper. I'm not going to go into a lot of details of the next paper, but I will explain the next paper's structure at least, and then we're going to talk about some issues that we mentioned here. Okay. Okay, the next paper is by Gerchak and Weng. This is 2004, and this is, I think, the manuscript was an older manuscript, so it had different versions. So certain things that I'm going to describe might not be available in the finalized version. There were, I think, they had a lot of similar things in the paper, and when it finally became a paper in a journal, it turned out that certain parts were cut out because it was very long, so on and so forth. So, but I think I will be probably talking about the paper. Now, the environment is very simple. This is the environment. We have an assembler, okay? And then we have a number of suppliers to the assembler. Now, for the assembler to complete the assembly, all the suppliers should supply some parts. Now, let us assume that we have 1 unit of this supply is going to be used in 1 unit of the assembler. It doesn't matter, but you can always like change the units and play with it. So we will have unit-to-unit correspondence. So it turns out that, of course, you are going to need 1 unit from each supplier in order to complete your assembly. Okay, so this is the situation. Now we are going to have f of x and capital F of x as the demand for the assembler, stochastic demand, and let's say that we have n suppliers. Now, we usually call these as components. So we are going to have n components assembled finally to meet the customer demand. Now, we are going to have, these are the definitions. CI is the unit cost of the component I. C sub 0 is the cost of assembly. And QI is the number of units of component I, which are going to be bought by the assembler. And Q sub 0 is the production quantity of the assembler. So Q sub I, in general, I from 0 to n, are the production quantities. Let's say that we have no holding cost. Or no penalty cost for not meeting the demand. But we are going to have R, which is the unit revenue for every unit that you sell. And without loss of generality, we are going to set R equal to 1. In other words, I am going to rescale everything so that the selling price is 1, so that we are not going to have a lot of notation coming into picture. So it means that all the unit costs are going to be much, much less than 1. So summation of C0, C1, C2, all the way Cn should be less than 1, so that there will be some kind of a profit in the system. Okay. So this is more or less the system that we're talking about. Now, the critical issue here is as follows. Now, these suppliers are independent. The component suppliers are independent from the assembler. If they were dependent, things would be much simpler, of course. So, question is, there are some logical things that we want to have out of this system. Number one, of course, I want QIs coming from different suppliers to be coordinated. In other words, is there any meaning of buying 10 from supplier 1 and 12 from supplier 2? No. But the problem is, because basically if you buy 10 and 12, then you can only assemble at most 10 units. The other 2 is going to remain. But the question here is, of course, you want to make sure that the suppliers are economically acting, which means that the quantity that you order from them and the profit margin that you give to them is reasonable, so that they will accept that quantity Q as their optimal quantity and supply you. Otherwise, they will be reluctant to supply you because of the loss that they are incurring when they are satisfying your demand. Okay? So we have to make sure that those Qs are in line, but it's not that simple to make those Qs in line. Always. So this is the problem that we have. And we are going to define a certain contracting scheme between the assembler and the component suppliers. And we will show that that contracting scheme is actually yield us the centralized solution. So this is what we are going to do in this paper. Okay. Okay, first let us talk about the centralized system. Now, when we're talking about the centralized system, of course, you immediately write Q1 is equal to Qn, and that's also equal to Q0, because there is no meaning for ordering more units, because it is going to be suboptimal. So given this, then the pi of Q centralized, so this pi is the expected profit of the centralized system, because it is Q sub C. So this pi is an expected profit function. So this is going to be equal to the expectation of the following quantity. Now, what will be the total cost incurred? Now, the total cost will be summation I from 0 to n, Ci times Q. So let me just write QC here. Okay, because QC is going to be, in this problem, the quantity that I'm looking for, centralized. This is the cost that I'm going to pay. And then what do I have? I am going to sell the items, and I'm going to sell the minimum of D or Q. So I'm simply going to take this expectation. Okay, this is another way of showing the same problem. Now, R is the revenue that I receive, but it's 1, so I don't write it explicitly. Okay, so R is 1. So now I can write this explicitly. So this is going to be QC minus QC summation I from 0 to n Ci. Okay. And then how am I going to take this expectation? This expectation is actually the integrals that we are more familiar. So this is going to be simply summation from 0 to Q sub C D f of x dx. This is the revenue that you are going to receive. Note that we don't have any salvage value, we don't have any salvage cost, salvage value, or goodwill cost. But it doesn't matter actually. It only extends the parameter set. Usually the results are not going to change. And then you have from QC to infinity, you are going to have Q times f of x dx. So I can now rearrange the terms a little bit. So this is the news vendor problem again. Note that the starting point is always the news vendor problem. Excuse me? Oh, this should be QC. You know what that Q is? That's Q. Yeah. We have Q sub C. Okay? All of them are Q sub C now. Am I right? Okay. Am I missing something? No. This is also C. Not a good one, but okay. Okay, this is a news vendor problem, but we're going to have sort of, because of not having the impurities and R being equal to 1, let me define F bar QC as the complementary cumulative function. Okay? We are familiar with this notation. You're going to have an exam next week on that. with complementary cumulative functions. I don't know. So if I rewrite this, this is going to be pi QC is minus QC summation I from 0 to n C sub I, plus I will have 0 to QC x f of x dx plus now I have QC f bar of QC. Okay? So just I introduced this notation. Of course, we have to assume that summation I from 0 to n Ci is less than 1. Otherwise, it's not a meaningful problem because nobody is going to operate. Because it means that there is no surplus in the system. Okay? Which is always the case, of course. And then we can obtain f bar of QC optimal to be equal to summation I from 0 to n C sub I. Okay, so this is the solution that we obtain. Okay, well, how do we obtain this? Well, we're going to take derivative. We're going to take derivative with respect to QC. So here, this is going to be minus this term. And then I will have QC f of QC here coming from this term. And from here, I'm going to have f bar QC minus QC f of QC. Those are going to cancel. So f bar QC is equal to summation I from 0 to n. Ci is going to be actually what we have eventually. So this is going to be the optimal centralized Q value that we want to attain in this problem. Now, if you now plug this back into this function, then pi of QC optimal is obtained as 0 to QC optimal x f of x dx. And this turns out to be the expected profit. Okay, so actually all the terms are extremely simplified when you have r is equal to 1. And the structure becomes very easy, actually, when you don't have any salvage, so on and so forth. Okay. Now, the reason that we are having this form is, of course, we are going to play with this form. Now, let me explain. Well, I think I better do that on Thursday. Now, let me explain what we are going to do, at least. We are going to talk about 4 different types of decentralized systems. We're going to talk about 4 different contractual situations, which is going to be operated by the system. So we are going to consider 4 decentralized systems. Number 1 system, we're going to have the so-called basic revenue sharing contract. Now, I will explain what I mean by revenue sharing. The second one is we're going to have the revenue sharing contract plus surplus subsidy contract. Now, what do we mean by surplus subsidy? For the items which are not sold, okay, the assembler is going to pay some money back to the component manufacturers, because they are only getting a share if item is sold. If item is not sold, they are not getting anything. So they are going to be subsidized, and this is called surplus subsidy. And then we're going to have a third one, which is the wholesale price contract. So this is the traditional one. Okay, you simply buy items from the assemblers, and that's it. And number 4, you're going to have the wholesale price plus surplus subsidy, or wholesale price contract with buybacks. Okay, in this case, some items are going to be bought back by the retailers. So we're going to have 4 different contracts, and we're going to see some results on these contracts. So the paper is actually related to getting the results of these contracts. Any questions on this? Okay. And in each of them, we're going to talk about actually a Stackelberg gain. In other words, the leader is always going to be the assembler. And basically, the assembler will try to get the system optimal solution by imposing certain structure in the contract. So this is what we're going to see on Thursday. Any questions? Okay, I'll see you on Thursday.